If we go back uh, to the binding energy curve, what we observed is that probably the nucleuses that have mass number less than 30, uh, and those nuclei who have large mass numbers, they are unstable. Because why they are unstable? Because their binding energy per nucleon is less. Now, to account for it, if we could go with more reasoning of nuclear instability, there are two major forces that we have inside the nucleus. The very first force is electrostatic force, and this force is repulsive because we have only protons inside the nucleus, and uh, and these protons in the nucleus, they are certainly trying to to move away from each other, if they are the protons, and they are trying to actually fly off due to this force. And then we have the nuclear force, and this nuclear force is attractive, and and this force is because of exchange of particles known as mesons. And what we have inside the nucleus is protons and neutrons. So so till now, what we say is that we have electrostatic force and we have nuclear force. Now, the nuclear force is a short range force. We know that it is effective only if the nucleons are at a separation of 10 to the power of minus 15 meters. Only then this force is effective. And it is practically zero as it crosses 10 to the power of minus 15 meters. So that's why it's also called as saturated force. And when when the now when these nucleons are far apart, when they cross this distance, this force dies instantaneously. And moreover, the nuclear force between neighboring nucleons is it is more than between the two nucleons lying on opposite edges of the nucleus. Certainly, it should be the case that I'm trying to tell. At the same time, if we go to the electrostatic force, this is repulsive force, and it is long range force. And nuclear force is it's short range. We could see it. It's short range force. So we have this electrostatic force. It is long range force, and in small or light nucleuses, maybe this nuclear force is the nuclear force is large as compared to the electrostatic force of repulsion. So we have a stable nucleus, and and that's why the nuclei that fall within that range that we have seen from binding energy curve, they happen to be stable. And on the other hand, in the large nucleuses, having a large number of nucleons, the nuclear force is small. So this nuclear force is small compared to the electrostatic force of repulsion. Hence, we can say, on account of these two forces, we can say that these nucleuses whose mass numbers are large, they are unstable. Now, another way of explaining this fact is the presence of neutron. The presence of neutron inside the nucleus. The presence of neutron. And this neutron plays an important role in nuclear instability. And what we have is the nuclear force between a proton and a neutron. is greater than that of electrostatic force. Okay, that's what we have. If we talk about the light nuclei, they are stable, and as this mass number goes on, as this mass number increases, what we have is the number of protons increase, and then the electrostatic force of repulsion between the protons. So when the mass number increases, we have a more number of protons, and this results in more and more repulsive force. And in this case, the nucleus should not have existed, since a nucleus having large number of protons, they exist in the form of uranium-235, or with mass numbers 92. Okay, so the electrostatic force of repulsion between the protons is compensated. It is compensated how? When the number of neutrons in the nucleus increases. So, if you have a mechanism where the number of neutrons increase, this increase in the number of neutrons leads to less electrostatic repulsive force between the protons. So, this is why in large or heavy nucleus, which have more protons, they provide extra neutrons. They provide these extra neutrons in the nucleus, and thus a large or heavy nucleus has more neutrons than protons, and these excess neutrons provide an excess. You have excess neutrons now because you have nuclear force between neutrons, and this force is attractive force. So what does it mean is that if there is conversion of a proton into a neutron, we are decreasing the quantum of electrostatic repulsion. At the same time, the nucleus is attaining stability by virtue of a neutron, because there is the force, attractive nuclear force between the neutrons inside the nucleus, and this may be the reason that this excess of neutrons provide the extra nuclear force attractive to compensate the electrostatic force of repulsion. Now, a nucleus becomes stable if the number of neutrons that we have is equal to the number of protons. So number of neutrons equal to number of protons. Okay, so therefore for a heavy nucleus to become stable by converting a neutron into a proton, by emitting some beta particles, okay, by emitting some particles and antineutrinos, so that till a number of neutrons comes equal to the number of protons inside the nucleus. Thus, heavy nuclei are unstable. So they are unstable, and they always try to attain some kind of stability, where we have the conversion of these neutrons into protons, and this kind of thing leads to breaking down of a nucleus which is unstable by emitting some kind of particles from the nucleus, and the parent nucleus converts into the daughter nucleus. So these could be some of the basic reasons that I try to talk about here, that why we have instability, why we have their instability in the nucleuses, in certain nucleuses. And certainly we call those nucleuses as radioactive nucleuses, because they are unstable and they keep on breaking and emitting radiations, emitting particles, and converting themselves into some daughter nuclides.